On the back of those, on the scrap paper, is a little flyer about a class I did in software design.
Oh, cool.
And that was a week ago, but it's on YouTube now. So
awesome.
if
Thank you.
You want to search for software design GJMAKERSPACE, and it'll be the first item.
Yeah, I'll check it out. Thank you.
Oh.
And it's has the added benefit of it's a cure for insomnia.
No, I'm sure
So
not.
that talk got recorded?
I did.
He
I
recorded
it.
the audio. It's audio.
I
only,
recorded the audio, but then I made slides.
Ah, yes.
Okay.
I
And
did
so,
go
and
with
it's
that.
it's a little weird because the slides were made after the lecture, so in some ways they synchronized too well. Anyway, let's set this dumpster on fire.
Sweet.
Okay, so my name's Tom, and I taught AI for 15, 20 years, something like that. And this is going to be an overview of AI. So before we start, let me just get everybody's background. I know you're a neuroscientist.
Yeah, I don't know if I'm a neuroscientist, but a little.
Okay, and we're going to talk a little bit about that when we get to the section of neural nets. This is an overview of AI techniques. And the second one we get to is going to be neural nets, and we'll talk about its relationship to neuroscience, because it kind of stretched and broke. That it started with computer scientists and neuroscientists, and then at some point the neuroscientists said, hey, that's not the way it actually works. And the computer science, hey, we think this is cool. Kept on going. So I'm not sure it's that good as a model of computer science. So AI, what is it? I don't know. Any kind of clever algorithm that doesn't do exactly.
Come on in.
You're only 10 seconds late, so aside from the introductory
Why don't
jokes.
you grab a seat so you can see the projector?
Thank you.
Yeah.
So this is the first slide. The last slide, that was the last slide. So you're right here at the beginning. Okay. So AI, what is it? I don't know. Any kind of clever algorithm that can fool you into thinking that it's smart. Sort of. How does it work? We're going to talk about that today. We're going to go over a bunch of different techniques of AI and give you a quick overview without getting too technical on how they work. Strong versus weak AI. Okay, strong AI is like what you see in the movies. Like the robot goes to the UN and sues for human rights.
A lot of Asimov books and that.
Yeah, Asimov's books and all of that. If I'm going to talk about that, I prefer to do it at a bar and drink a lot. So it's not really what I do.
Not here yet.
I do the weak AI. If I can get the thing to play Monopoly, that's good. It doesn't wake up in the morning and decide, I don't like Monopoly, I'm going to invent my new game. I guess maybe it could, but or I don't like working for you. And actually, I've had plenty of programs that refuse to work for me, but that's another story. Okay. So what we're really covering here is weak AI. Strong AI, in theory, can come if we can understand the brain completely. See, right now it's a little mysterious. And if we could understand it completely, and if we had the power to model it, I guess in theory, you could have a mind, really. But even weak AI seems to be struggling a bit in certain areas. Certain problems are NP complete. So as they start scaling up, it means they don't work anymore. That's what NP complete means. And but that's what we're going to talk about, weak AI. And we're going to do three categories of AI, and there's a lot of subcategories within this. But this is the classic AI, finite state machines. And then we'll get to classification. This is how Amazon figures out what other books you want to read and, you know, stuff like that. And finally, optimization. So what's the best you can do in a certain situation? Like, where should you put the dials to get the maximum out of a system? Financial systems or nuclear plants. Very scary, actually. But in any case, those are the three basic subjects. And we're going to start out with finite state machines. So, and the question is, it gets a little philosophical. Is the universe a finite state machine? Maybe. The whole idea of a finite state machine is that you're in a current state and you take some action and that takes you to a different state. So, and if you took a different action, it would take you to a different state. You could argue that the universe is a finite state machine. We use the term universe to cover whatever our domain is. So if you were writing a program to play chess, that's your universe. And moving a piece on the chessboard does in fact put the universe in a different state. Now, chess, checkers, a lot of games are finite state machines. You know, they go from one state, you take an action and they become into another state. So, but whether or not the universe is a finite state machine, I don't know. So this is how we represent finite state machines. There is a mathematical representation, I'm going to skip that. But essentially the little spots are states. One of them is marked with a double arrow. And that's the initial state. That's the state that the universe starts out in. Or it could be thought of as the state the universe is currently in. And you take different actions and it would take you to this state, and then another action would take you here, and then another action would take you here, another action would take you here, and then you've lost because there's no way out of this state, and it's not a solution state. We put a double circle to mark the solution states. And so the goal of the AI is to tell you what actions you need to take in order to get from your initial state to a solution state. And this can be used to solve problems like Sudoku and a lot of simple puzzles. For those familiar with graph search, there's two main methods, depth first search and breadth first search. Unfortunately, as the graph increases in size, the time that it takes to search the graph increases exponentially relative to the size of the graph. This is why the history of the military funded a lot of AI, and then they got to a point where they were really annoyed. They figured, well, okay, so they've demonstrated that it solves small problems, and they need a bigger computer in order to solve bigger problems. But getting a bigger computer only increases your capabilities on a linear scale, and the problem increases on an exponential scale. And so then the military went through a phase where they were no longer funding AI. But now they're back to funding it.
So that means there is something that's even too expensive for the military.
Something too expensive? Is this my brain?
Yeah.
Something too expensive for the military?
Yeah. I mean, you know, we all anecdotally hear about, you know, $6,000 toilet seats and, you know, and that kind of thing. But even the military has their limits on spending.
Yeah, their limit is set because if you're a company that makes weapons then there's a good chance they can retire out of the military and come to your company. So the funding may be unlimited for companies, but it's unlikely that they're going to retire out of the military and go to academia. So the funding for academia to do research may be more limited or more pragmatic. I'm not sure. Anyway, depth first search and breadth first search are blind searches. So you're essentially just going through this graph, hoping to find a solution state, and that's not really AI. To use AI, to be called AI, you have to have a heuristic function. And the heuristic function gives you an estimate of how good a node is. And so it might estimate for this node that it's 2 jumps away from a solution, and it'll estimate for this node that it's 1 jump away from a solution, and therefore it would prefer going to this node. And it's sort of a pruning of the, it's not searching everywhere blindly, it's deciding which ways are more likely to reach solutions. Now, it keeps these in a boundary so that if at some point it went down this route and the estimate was that it was a good node close to a solution, but in fact it didn't work out, then it would keep the other nodes that it had looked at sort of in a queue, and when this path got to a certain level of expensiveness, then it would revert to searching these other paths. But that's the basic idea. See, the idea is that you want a series of actions that will take you from an initial state to a solution state, and every action, it depends. If it's chess, every action is 1 move, so the cost is 1 turn. But if it's a lot of other operations, different actions would have different costs, and therefore you're looking for the cheapest cost. So the optimal solution, or maybe not. And then your definition of optimal, this is used for business planning and even military planning, in the sense that your initial state might be that you have troops scattered all over the world. And then your solution state is to have 300,000 troops in Kuwait. I'm not advocating this, I'm just saying. And it might be easier to get them in than get them out, but that's another subject. So you could take all the different possible actions that you might take, right? And the action might be send a transport plane to Worth. I'm not even sure if that may just be the name of the town, and pick up so many troops and take them to Wiesbaden, Germany. Okay, and that action would change the state of the world, because the state of the world is where all your troops are. And it would have a certain cost. And if you're the military, it might not be money. In a military situation, it might just be time. You know, regardless of expense, you want to get them all there. There could be trap states too. Get them all there, but without their weapons. That would be a bad situation. So all the moving around and stuff that gets done should eventually lead to solution states. People do this, people figure this out on their own, but it might be suboptimal, and the idea is it's a complicated process, so you have a computer do it. It might be a little more complicated than this, because you might be able to take multiple actions at the same time. So there might be a multitasking version of this that would optimize in parallel all the actions that you take. Anyway, this is the classic AI. This was the AI from the late 50s and the 60s.
As the variables increase, though, then
Yes,
that's why they're getting more into AI.
Yeah, you get a
Standard footprint.
you get 1,000 nodes. You know, that thing was what, about 10 nodes? So if you go 1,000 nodes, now that's
Well,
100 times bigger, and it increases with the square. So instead of being 100 times longer to solve, it would be 10,000 times longer to solve. And 10,000, you know, 1,000 nodes might not be big enough.
well, if you think of the military, U.S. military around the world, you're talking so many variables, equipment, people, everywhere.
We're going to talk about this. This doesn't even account for enemy actions like shooting down a plane. So, and we're going to talk about that. Two-player games where there's somebody taking moves to change the state of the universe contrary to what you want. And to tell you the truth, we do examples like chess and checkers where the people are polite and take your, you know, it's your turn now and it's my turn, you know, back and forth. In which case, I guess I'm getting to the problems. Yeah, adversaries in multiplayer games, chance events, okay, just even to play backgammon. You don't know how the dice are going to roll. If it's checkers, you know, there's no hidden information, so it plays pretty well. By the way, in multiplayer games, the thing is solved the same. You just, well, if it's turn-based, then the way you do it is you'd say, okay, I'll start, it's my turn. So I would pick which one of these three the heuristic says is going to leave me in the best position. And the heuristics is sort of where the secret sauce is. You know, like for a chess playing game, there's a simple heuristic for chess. You assume that the board is to your advantage. You count 7 for the queen, 5 for castles, 3 for bishops and knights, and 1 for each pawn. That would give you a way of scoring the board, like whether or not it's to your advantage or to their advantage. That's not a very sophisticated way of scoring. There's more sophisticated ways. There are pieces in the middle that are attacking more spaces are more valuable than a piece that's stuck in the corner without anything. Also, controlling the center of the board is another way, and you make sophisticated scoring systems, and that's how was it Deep Blue beat Kasparov or whoever it was. So it's actually they actually cheated. I used to work for IBM, but they cheated a couple of different ways, but I don't want to. This is being recorded now.
But it's legal cheating.
What's that?
Legal to cheat.
When you're in a tournament, you get to see your opponent's previous tournament activity. And so Kasparov asked IBM, could I see, you know, how it's played previous games? And IBM said, yeah, we'll show you that, and never did. And then they went to the rules. The rules are that you get to see previous tournament games and it had never been in a tournament, and they delayed it to the last minute, just saying you'll get it, and then they say, well, here it is, it's nothing.
Well, they were looking at every previous game that ever existed, probably.
Oh, of his. Oh yeah, they have the capacity
They were there, big advantage
to test that. Sure. The other thing is, the story is they fiddled with the algorithm between matches. Which means that you're not just competing against the computer, you're competing against humans as well that are tweaking the computer. Anyway, he got very upset, and my theory was they offered him an extra $1 million if he'd throw a tantrum. Because they gave him $1 million to play, and it was great PR for him to get all upset. And that was my theory. They gave him another $1 million to get upset. But in any case, if it's a multiplayer game, then what you do is you say, well, I'll pick the heuristic for the best move that I have. And then I'll assume that he'll do the same. So from the position that you go to, you decide whether it's what the worst is for you. And then you keep doing that. You keep alternating. So I'll go to the best, then I'll go to the worst, then I'll go to the best, and I'll go to the worst. And you try and find a solution path in that way. Now, there's no way of telling what the opponent will do. And so, but if he doesn't do what's worst for you, then it's still to your advantage. You see, you just start up the whole algorithm again each turn. So if you figured that this would be the worst square for the worst position for you, and you assume that he took it, but he doesn't, he goes here, so that's fine, now you're here. You start the whole algorithm again as if this was the initial state, and that just puts the advantage to you. So if he doesn't do what's optimal for him, that's all the best for you. So that's essentially how we deal with two-player games.
Obviously, you're talking real time. You're not talking something that's fixed. It's the variation every second or whatever, depending on
Yeah, the limit of a chess playing program is how many moves ahead can it look. And also, the total number of states in the universe is too big to fit in any known computer. And so what you do is it's like a truck that's rolling out its own pavement. So you start from this initial state and you calculate what your future states are possible. Then you calculate the future states from there and the future states from there. And I had a program called Sargon that ran on a 6502 and would beat me steady at chess, and that's when I quit playing chess. Because I knew the 6502 was just like a little 8-bit thumb twiddler, and it was beating me consistently, and I lost all interest in playing chess. But you could set it to how many moves ahead it would look. So you could set it down to looking 2 moves ahead, and then it didn't play very well. Or you could set it to moving 8 moves ahead, and then it just took forever. But it would play a really good game. My game was actually to wait for other people to make mistakes and then pounce on them, which makes me a bad player against computers because they just don't do the mistakes, right? So you can't capitalize on other people's errors. Now the other thing is, in a game like backgammon, you'll have random events like rolling the dice. It becomes like a 4-player game. There's the dice's turn, there's my turn, there's the dice's turn, there's my opponent's turn. And it keeps repeating like that. And so when you roll the dice, that creates like its own states. And you can get into probabilities now because you can get, well, what move is going to be the most probable for me to win, because he might get a lucky roll or something. And you consider the 36 possible combinations of 2 dice. So it has 36 possible outcomes that it can do, each of which creates another state in the universe, and then you continue playing on from there. I had a class and 2 students actually made chess playing programs. And so we made a big deal. We're going to get the class together and we're going to actually pit them against each other. And we had a chessboard, and they both ran their programs independently. So they would have to manually put in the move from the other player. But there was some rule that one of the teams didn't implement. It was either en passant or castling.
Uh-oh.
And so the other team castled, and that team couldn't put that in as an input to their program. So, I was looking forward to, having a really fun class, but it was about 2 or 3 moves in that the whole thing sort of fell apart, and I had to improvise, what I'm going to do for the rest of the class. Which...
Give him a handicap.
What's that?
Handicap 1.
Handicap 1?
Well, you can add points to the person who has
It could no longer play
good play at all.
because it couldn't represent that state
I see.
that the universe was in, so it couldn't make any choices. And I tried to get the other team, well, like, okay, we'll just make new rules, no en passant, but they couldn't reprogram their system fast enough to.
And my guess is that neither team, their programs allowed you to enter an arbitrary initial state. They only allowed the standard initial state of a chessboard. Because if they would have allowed you to enter an arbitrary state, well, you could have just started a new game with the state.
With the castle and the king and that. Yeah, they did not account for that. Anyway, that's it. A-star search is sort of the king of searches. It only requires that the heuristic function never overestimate the remaining cost to the solution state. So it's sort of like the Price is Right. You can't overbid the price. So if you can guarantee that the heuristic function doesn't overestimate the remaining cost, then you get the advantage of guaranteeing that it'll find the optimal solution. Because at every point it considers the total cost, well, total estimated cost of a solution at any given node is the cost of going there so far plus the estimated cost of where it's going. And if it never overestimates, then you guarantee that you'll get the cheapest solution. And by the way, to never overestimate it, just say the cost is 0. That is a valid, that's a valid heuristic function, but then it reverts to just being breadth first search. And so breadth first search does find the optimal solution, but it's slow. And so anyway, so that's pretty much it for the, that's it for it. And now we're going to get into neural nets. That was your field. So.
I have a quick question. I read about NP hard problems once, but can you? I know that you have a note in there. It's about having to go through each potential pathway sequentially or something like that, right? Like you can't. And you were alluding to it when you're talking about exponential time or computer.
NP stands for non-polynomial.
Okay.
And so at a certain level, we have this thing of classifying how long it takes to do things. There's two types of sorts. One goes up with the square of the size of the thing you're sorting. And another one goes up with n times the log n. And those are the good sorts. So you have the good sorts and the bad sorts. Usually the ones easy to program go up with the square, and the ones that are harder to program go up with the n times the log n of the number. Now, those are polynomial, and some polynomials are scary, like n to the 1,000th power. It's still a polynomial. But we don't run into those. Most algorithms don't end up being n to the 1,000th power. It's usually n cubed or n to the 4/3 power, or n to the 4th power maybe, And of course you can always contrive things. But what we're scared of is 2 to the nth power. That then is not a polynomial, that's an exponential operation. And problems that are NP complete just don't scale well. Yeah. You increase it by 1, you've doubled it. You increase it by another 1, see 2 to the nth. So if you have 3 elements in a graph and you say, 2 to the 3rd power, that's 8. No big deal, right? But if you just increase it by 1 node, now it's 2 to the 4th power. So then there's the story about the guy who invented chess, and he wanted from the king, he wanted 1 grain of rice on the first square, and 2 grains of rice on the second, and 3 grains of rice on, or 4 grains of rice on the third square, and 8 on, and so forth. And the king said, fine, and ended up having to execute him because, you know, the embarrassment of not fulfilling a promise for the king. I don't know why the other guy would get executed, but anyway. So yeah, NP. Now, then this was what the military ran into. They just go, oh, we'll use supercomputers. Supercomputers at the time were just, they'd have like 1,000 CPUs or something. But that only increases linearly. And so no matter how much you do, when this problem gets big, you're out of luck. We're coming to a thing called quantum computing, where the bits are superpositioned, so it's 0 and 1 at the same time, which means that if you have a 64-bit register, it holds 2 to the 64th possibilities, and so we get in that exponentiation back on the hardware side. So there may be hope for all of this anyway. And actually, okay, so while I'm talking, I'll just briefly do strong AI. There's a guy named Kurzweil who predicts the future and does pretty good at it. And he predicts that strong AI will come as a combination of 3 things. Quantum computing, because you get this incredible power of parallel processing, and evolutionary neural nets. Okay, so assuming the only thing we have as a concrete example of intelligence is humans and some animals too, and that's the mechanism is a neural net. Okay, and the mechanism that neural net was created was evolutionary. And I'm going to get to that because that was actually my research area, was evolutionary algorithms. And so Kurzweil feels that it's a combination of evolutionary neural nets and quantum computing that's going to get us to the point where, you know,
singularity.
Yeah, it is. He calls it a singularity. It's, you know, the point where they're as smart as we are. And of course, then they're working on themselves.
Yeah.
And so it explodes after that. So
that'll be an interesting day.
It'll probably happen in your lifetime, but not mine. Okay, so at risk of making a complete fool of myself, having a neuroscientist in the room, this is what a neuron looks like. The only thing that's really important to us is that it has dendrites. And these are inputs to the neurons that can either inhibit them from being excited or can excite them to being excited. I don't know if that makes sense, but they're either excitatory or inhibitory. So they either make this thing trigger or not. And then it has an axion that goes off, and then that causes it to trigger other neurons, because, of course, one neuron by itself doesn't do much. So anyway, oh, by the way, and yeah, this whole field, artificial neural nets, was started with neuroscientists, and the idea was we're going to model, you know, brains, or very small brains perhaps, or something. And then after a while, the neuroscientists go, you know, this isn't how they work. But by that time, the computer scientists were actually using these things for different things, and we're kind of in love with them, so it's sort of divided off. I think that's a field that still needs to be done, is the modeling of the way neurons really work. But the way these work is, it's actually very primitive. It's an artificial neuron. So it gets in numbers. So, and that should be WN, that's a typo. So it gets in a number, another number, it gets in multiple numbers, okay? And then those are all multiplied by weights. So there's some number that, and if that number was negative, so let's say this was -1, then that would make this an inhibitory dendrite. So it would likely to not excite this neuron. It would likely just, you know, make it not trigger. Okay, so you get all these inputs, they all go in, they get multiplied by the weight. This is very simple arithmetic. And then they all get summed. And then that's sort of the output, except that it goes through something called a squashing function. So the squashing function, the squashing function works like this. It's, I mean, there's different versions of the squashing function, but it's asymptotic to 1. So it approaches 1 but never gets there. And it's asymptotic to -1 here. So regardless what the x is, the f of x is going to be somewhere between 1 and -1. And this keeps this whole thing from running away, right? Because otherwise this thing could end up with really large values and then pass those values on through the neural net. And this thing just sort of squashes it. So no matter how big the numbers coming in are, which of course, these might be the inputs, or they might be from other neurons. If they're from other neurons, they'll always be between -1 and 1, so it's not a problem. But then they get multiplied by different values. They come out of the neuron, they go through the squashing function, and that's the output. So the output of every neuron is always between -1 and 1. Yeah.
Okay, so the reason for the squashing function is so you don't overload the network. If you go above 1, you get too big of a charge.
I'm not an expert on this. The way it was explained to me was that it keeps the thing from running away. See, because we're going to show that this is going to feed into another neuron, it's going to feed into another neuron, it's going to feed into another neuron. And we want to avoid, you know, hitting the limits of the size of numbers. You know, there is no infinity of numbers in the computer. There's some maximum real value. It may be really big, but we want to avoid that. We want to keep this whole thing sort of tamped down. Otherwise, when we get to a network of neurons, if one of them is just exploding with high values, then it'll swamp all the others and make their output meaningless when it gets added in to go to the next layer of the neurons. So anyway, that was one neuron. This is a neural network. Yeah.
Yeah, I was just wondering if you could talk about the weighting of
Sure.
each dendrite and how because when a neuron fires more, it's going to be probably stronger. So like the weights may change over time, but I'm not sure. Like, yeah, how do you set the weights?
That's a great question. I will get to that. That's 2 slides away.
Really awesome.
So you have input. I worked 13 years for an investment bank, Japanese investment bank, making trading systems and stuff. So this could be anything. This could be the price of gold, the 10-year interest rate, the 1-year interest rate, the S&P 500, whatever it might be. And the idea would be that all these would lead into weights. And this only shows one hidden layer, but there could be many hidden layers. And then their outputs would all be calculated and go into the next one and go into the next one. And finally you'd get to the output. And the output, it could be binary. It could just be buy or sell some particular thing. So time to buy the Dow or the S&P 500. Could be a signal, right? Or it could be a weighting, like to optimize a portfolio. You know, it's like more bonds, less stocks, or whatever it might be. So
Did you find that neural nets did work in the stock market? Because
Never actually did that.
Huh?
Never actually did that. I'm experimenting with it now, but that wasn't what I was doing for the Japanese investment bank.
A lot of broker, whatever, investment banks have been trying to use neural nets for years.
Mm-hmm.
I just wondered if they were more successful than traditional tools, but I mean, presumably they're supposed to be because they're smarter.
You know how you can tell whether an automated trading system works or not?
No, I'd like to know.
If it works, nobody will tell you about it.
Yeah, you'd never find it, yeah, that's right.
And we even joked about it. It's like, we'd say, well, if it doesn't work, we'll sell it. But, you know, and there is no logic that would, for somebody to sell you a working trading system.
I wonder how many.
I mean, the people who do sell trading systems, the story's always the same. I've made so much money and now I want to help you.
Yeah.
Screw you.
There's always a new guy.
Screw you, you liar.
Yeah. How many neural nets predicted gold at 1,500 now and stuff like that?
Yeah, and my PhD advisor was always wanted to know when it was ready to actually start trading. And I told him, your money right away. Anyway, that's a whole nother thing. I got to do a class on that, trading systems, but I don't want to do that now. And I actually avoided it in my PhD dissertation. A lot of the dissertation was about creating synthetic systems to try and predict what the synthetic systems were going to be, because I didn't want to go down that path of talking about financial analysis. I think it's mentioned once at the end that this thing might be applied to financial analysis, but it was done very clinically without, involving synthetic functions that it was trying to predict, which is a whole nother thing. So, but in any case, yeah, so then the question is, if all the weights were exactly right, then presumably you could get the inputs to come up and tell you, how much bonds to have, how much stocks to have, or whatever, presumably. Actually, probably the best it could do is tell you what was most likely to be a good idea. Now, how do you get those weights to be right? Well, you start out, you just randomize all the weights. Then you put in the inputs, and lo and behold, the output's wrong, right? So you see that the output is wrong, and then you go and adjust all the weights. So if the output of this was positive, and this thing ended up being positive but should have been negative, then you would adjust that weight to a lower value. And if the output of this was negative, and the output of this was supposed to be negative, then you would adjust that weight to be greater, because it would be more. And you want to adjust it by little tiny bits. And so this is the training process for a neural net. So you keep running lots of inputs for which you know the outputs. So in the case of financial stuff, it would be historical data.
Yes, sir.
And then from the outputs, you adjust these weights. And this whole thing, it's called back propagation because it starts from the back and works to the front. Because just like this, maybe this should have been higher, so its weights get adjusted, and so forth on down the line. This is one of the advantages of the, I'm going the wrong way. One of the advantages of the squashing function is that the derivative is known. And so if you're way out here a small adjustment in x won't do very much because you're asymptotically closer to 1 anyway. So if you're way out here, you know what the first derivative of this is, and so you can adjust it better, and that's part of this. There are other squashing functions. People use a squashing function that looks like this. So it's just a ramp here, and then the idea is, well, if you're over here and it's too high, you know you have to move all the way over here somewhere to this line. But I don't remember all the math, but if I'm not mistaken, the derivative of the squashing function is almost the squashing function itself, with just a little modification. So my first degree was in math, but I was pretty bored with it by the end. So all my master's and PhD were both in computer science, with which I've been fascinated. In any case, you use that derivative to figure out how much the weight should change, but you don't change it a lot, because then you can get these wild oscillations that are not useful. You want it to train in slowly. So you might there's something about, like, you save the last change as well. And so you avoid getting this thing, okay, I reduced it last time, now I'm going to increase it, reduce it, increase it. You can get into this oscillating thing. So you avoid changing it more than 1%, and you avoid, and I don't know, that 1% is just an arbitrary value that you might plug in and try this out with. And so after you've trained like thousands of days of past data, this thing would start to get better. But then you'd retrain it, and you'd keep adjusting the weights a little bit at a time. And the idea is that you get them down to the point where they're making accurate predictions. At least they were accurate in the past, but as your broker may have explained, past results don't necessarily indicate future, whatever. But it's the best you can do.
You could certainly eliminate some pathways, though.
You could, because the weight could just go to 0, and then you're essentially saying that dendrite is blocked off. There's many topologies. The classic topology is to have an input layer, multiple hidden layers, and finally an output layer. And it all goes in one direction. But that doesn't mean that's the only topology. And the idea is every node in every layer goes to every node in the next layer. And that, again, doesn't mean it's the only topology. This is not science. This is alchemy. And so there are no rules, you know. That is probably something that the neuroscientists didn't care for, was that every neuron hooked to every neuron in the next layer. Well, that's not realistic. There are other ways of adjusting the weights. One of them would be to use a genetic algorithm. So you would have, like, well, I'll talk about genetic algorithms later, and I'll try and tie it in to how the neural nets would work. And that, like Kurzweil was saying, is going to be where real intelligence comes from. Anyway, backpropagation is what I described. That's the classic way of training a neural net, and that's the classic way of adjusting the weights and eventually getting it so that you reach some level of accuracy that's acceptable for whatever your situation is. This is, by the way, this is how speech-to-text works, and also handwriting recognition done with this. Scanners that you scan in printed stuff, and then it gives you the text in ASCII, are done with neural nets. So apparently it does work. Evolutionary systems. Okay, so this is like dessert for me because this was my research area. There's the grand old man himself, Charles Darwin. I don't know what this picture has to do with anything, but looks like a lot of humans. Well, whatever, who knows? There's two basic types of evolutionary systems, genetic algorithms and genetic programming. This is where I stole the slides from another presentation. Okay, Darwin's principles is essentially that useful attributes will inherit to the children to some degree, and there's not enough resources for everyone in the population. So somebody's got to die. Evolution is pretty cold.
Scarce resource.
Yeah. It's not actually, I would say the more competitive it is, maybe the faster the evolution will take place. So if there's only enough gazelles to feed 100 lions, but they have 200 offspring, then some aren't going to make it and some are going to make it. So the attributes that make them, better at hunting gazelles are going to be more likely to survive. There's big probability elements in this because you can be the strongest wolf with the best eyesight and the biggest teeth and the sharpest. You can be howling at the top of the mountain and lightning can hit you. So there's no guarantees in life. But it's over large populations, the attributes that promote survival. It's actually more complicated because they have to promote survival and mating. If I had a mutation with a third arm that came out of my top of my head, that'd be really useful for soldering. But, maybe no one would like that. And so it's a selection for survival and a selection for mating. And this is what confused Darwin about the peacock. Why the big tail? There's no survival benefit to having the big tail, but it turns out it attracts the females. It's the males with the big tails. Okay, genetic algorithm. The original slide was about GP, but it explains genetic algorithms.
Could I?
Yeah, sure.
Okay, on the evolution, a lot of new research that I read, everything, and when they're trying to figure out why they're left-handed people, what kind of survival mechanism allowed for 10% or whatever.
I don't know, but the Roman army put them on they would take the left-handed people and put them on the left side of the column. So there's somebody with their predominant arm with a sword sticking out.
Baseball, whatever. But I'm talking about way back when this stuff evolved. Why wasn't it deselected? And they really don't know that. And also, I was just thinking to myself, a sociopath, there's 1 to 3% of the population sociopaths. Why wasn't that deselected? We started thinking maybe there's an important reason for that. That's a lot of people. That's millions of people.
Well, some sociopaths are very successful, as Steve Jobs.
They definitely are successful. At the time,
there's
it might have been useful to be a sociopath.
Well, I am super interested in evolution.
I know.
I was into artificial evolution as a research area, but I read a lot about evolution, and I'm really interested in evolutionary psychology. Mm-hmm. So the idea is all our weird behaviors, can you trace them back to having some advantage to putting your genes into the next generation? And then,
like Asperger's.
Like Asperger's, which is on the rise now. It turns out, Asperger's, if you've ever taught in a computer science department, you will know that a certain percentage of the faculty have Asperger's. It's socially difficult for them, but there's some advantage in sort of logic processing or math processing even. There's a big rise now in Asperger's because it turns out that they're good at communicating electronically. If they're communicating by email, they do really well. And over in Silicon Valley, there's a big rise in Asperger's syndrome, and
Maybe they just migrate toward that nucleus.
Well, the idea is that they may be more successful now because it's given them some skill with the computer, perhaps, and they may be meeting other people. And these are people with functional Asperger's because it's all autism on a scale, but there's a higher rate of autism over in Silicon Valley, and so the theory is that two parents with Asperger's may be getting together and having children with sort of a full-blown autism. And I don't know.
I heard that it might be the next step in our evolution.
Anything's possible. I think that
if we have to speed things up, the way to do it is just expand one section of what the area we psychology.
Well, I know it's doing well in computer science departments. What do you think, Wayne? Got any people there with social difficulties, but a lot of skills? It's hard to say. It's probably more useful for research than teaching. We had a couple teachers that, would read the same PowerPoint slides, year. I mean, literally read them. This is like torture. But anyway, but we're successful researchers and we get a lot of grant money. So it's a high price to pay.
There's a lot of variability in the minds of people. That's one of the big, it's so much.
Well, in evolution,
Yeah,
in fact, one of the things that kills artificial evolution is that you get to a point where a local solution to problems has saturated the population with its genes. And then this prevents more evolution from taking place. So now you're locked into what may be a semi-optimal or a suboptimal solution, but it's a local optimal, but you can't break out of it because you don't have enough diversity in your population. This is something that happens with animals that are going extinct. There's not enough diversity in their population, and it gets down to a couple hundred people, a couple hundred species, individuals in a species. They're probably not going to make it because they're going to have to inbreed to such an extent that. Anyway, artificial evolution. We know that binary strings represent the solution to all problems on a computer, right? The solution is some binary string, whether it's a picture or a number or a string, ASCII or whatever it is. It's some binary solution. So you start with a population of random strings. And then you apply the fitness function to them. You say, well, how good a solution is this? Because you got to be able to score the solution. In financial analysis, it's real easy because it's how much money it made. Actually, that's not actually a good fitness function because it should be how much money it made relative to how much risk that it took. If it was bouncing you all over the place but it ended high, that's not as good as something that steadily went up but didn't go quite as high, because you'd expect that if you went with that strategy, it could bounce you around and leave you low. So So you apply to these random solutions, you apply the fitness function, and the ones with low fitness function, they die. They're removed from the population. Now, the winners will mate with each other and have offspring. And the offspring will have some of the binary solution from one of the parents and some of the binary solution from the other parents. Now, you're hoping that the good qualities of one parent will combine with the good qualities of the other parent, but there's no guarantee. You could get the bad qualities, my looks and my wife's brain, but if that gets back to her,
Yeah, your looks.
okay, so,
Well, sometimes
So-
you can trace back your ancestors, I think, anyway, my theory is. Once in a while, you get a lucky hit from some, like Lord Kelvin on our side and things like that.
it doesn't matter. You get the good combinations, you hope for the good combinations of both parents, but some children will have the bad combinations from both parents. But it doesn't matter. They're thrown into the population and the fitness function is applied to them. So it does not matter. And so over time, the solutions improve. It's just the way it works. You know, it can run into problems. If the population is too small, and depending how you allow things to work, it's actually a good thing. You know, a lot of my research was looking at natural evolution and seeing how that could benefit artificial evolution. Now the thing is we die. We have a limited time to procreate, and then we're out. Now the advantage of that is, okay, if that didn't happen, the whole world now would be saturated with Alexander the Great's genes. Him and Genghis Khan, I guess, would have all the, because they'd still be around, right? Still producing offspring, right? So there's an advantage to that. There's an advantage to dividing the population into two sexes. Normally we don't do that. We just take a random element of the population, mate it with a random element of the population, and not worry about dividing it into male and female. But the example would be in horses, there's one male stallion that mates with the entire herd. And he fights off other stallions and doesn't let them get to the mares. So the male role in the evolutionary process in that case is to provide more selection, because it's only the strongest and bravest and courageous horse that gets to mate. But the females, they all mate with that stallion. And so if one of them is smaller or has a thicker coat or whatever it is, they maintain diversity in the population. And so later, if there's a climate change or if there's a shortage of food, that would give an advantage to smaller individuals. Or if the climate changes and they need thicker coats or thinner coats or whatever it is, the females have provided that continuity, and you have to maintain the diversity in the population. There's some interesting things too. I did experiments with dropping the meteor on the population. So the population, the typical curve that you get is that things improve, and then they kind of level off. And at that point, my theory was, you drop a meteor on them. You kill 90% of the population, regardless of fitness. Okay, and what you get afterwards is some weird fluctuations. This was the good marker.
Well, until you keep using it long enough till it becomes a bad.
You know, the
mark.
trick is to balance them on the tip and let the ink flow down to the wick. But the curve you get is and you can either take average fitness or the fitness of the best individual in the population. They all make a curve that kind of goes like this, and then it levels off. And now you're getting saturation in the population. So you hit some local optimal solution, maybe not the best, but you've hit some local solution and you're just not breaking out of it. So you drop the meteor on it. Kill off 95, a large amount of the population. You get like these things, like suddenly it gets erratic and then it starts going up again. And so you sort of shake up the population. So
The S-curve might apply sometimes too, though. At the beginning, very slow development, all of a sudden the adaptability is there and the species starts to increase. So you have an S and then it levels out. So
running these things are like watching 3D printing. It's real dull.
I mean, idealistic.
You sit there, and you've got some hypothesis and you've got some experiment. So you're doing it with the meters or without the meters. And you tend to sit there looking at it, and then after a while you quit doing that. What's that?
Could be a volcano.
A volcano, yeah. So it's, sudden change in the environment, you're right.
It could be a small change too, a local island or something, right?
One of the reasons I think that evolutionary systems are good for building financial trading systems is because they do evolve and they are adaptable. So when the markets change and the interest rates drop or whatever it is, these things, other individuals suddenly will move to the forefront and start, manifesting.
Could be a black swan
too. By the way, it's not just mating. You need mutation as well. It's really strange because when you put in the calculations for mutation, they almost invariably are bad. When you mutate an individual, it almost invariably causes that individual to have a lower fitness. But for some reason, the evolution progresses better. So and if you think about it, the original binary strings that made up the original population may not include the right strings for the final best solution, so you need some mutation to go with that.
Well, I heard that, I'm sorry, that good enough, evolution doesn't necessarily develop the best solution, but a good enough one, survival.
Not the best, but better.
Yeah.
Better than, if you go back to what was that, the Cambrian explosion? All kinds of weird things. Snakes with three sides and things like that. And it wasn't that was so great, but it was better than other things. Trilobites were the big success. Now they're gone, but they were.
Every single one of them, which is crazy, isn't it?
I don't know. When I see a horseshoe crab, it sort of reminds me of the trilobites.
It's just that
They're not trilobites.
20 million of them are floating around, they're all gone. So it just,
Yeah, I guess they were the first animal with hard shells. I love that stuff, but I'm not an expert on it.
Yeah.
So that gave them a big edge.
A long time, and then
Yeah,
the meteor hit, and
something happened. Okay, so how do you run a GA? You create an initial string of random binary strings. You create the next generation, randomly select elements for direct inclusion, randomly select pairs for mating. The offspring have a combination of randomly selected parts of the binary string of both parents. select some elements for mutation, and rinse, slather, repeat over and over and over. You get some good solutions. Terminate when an acceptable solution is found, or when a maximum number of generations is reached. Turns out, if you don't get success with an evolution, just kill it and start over. You know, who knows? You know, there may, you know, if it's not working, it's not working. So don't, you know, the idea is, well, I'll just run it forever. But it's shown, and this is research people have done, better to kill off unsuccessful populations and restart them, and you'll get to a solution with less computational energy than just leaving one that's not working to just run. Those are genetic algorithms. That's the flow chart. It's really just what I said. They generate a random population, score the population. Have you found an acceptable solution? Success. Otherwise, have you reached the maximum number of generations? Failure. Otherwise, do straight selection, do selection for mating, do mutation, score the population, round and round and round you go. Eventually, you come out on one of these two.
Do you mind if we take pictures of your slides?
No, I mean, in fact, you can have the slides.
Oh.
So send me an email, I'll send you the slides.
Yeah, all right. I just, it's your property, and I just want to make sure.
What's your email?
It's actually on the last slide. Oh, that won't help. Well, you can copy it off the last slide. Genetic programming, this was my research area. So, I don't know if I want to get into this too much, but the idea is, well, a program is a form of a solution. In fact, it's the best solution you can have because it solves the general case as opposed to solving one case. You know, if you wanted to add two numbers, you know, you could use a GA and it would eventually, you know, find the right answer. But if you use genetic programming, it would eventually find a program that adds two numbers, and then that would be useful for other inputs besides the original inputs. So programs are sort of the best solution. I don't want to get too much into it, but all programs can be written as an S expression tree. And this is particularly true for the language Lisp, where everything is just an expression. Okay, so even loops and if statements can be put into a big expression like this. An S expression, this is an S expression, and this is an S expression tree. So this is a way of representing this whole thing, and essentially to evaluate, this is, you want the final node be evaluated, but before you do that, you evaluate its children. But before you do that, you evaluate its children. Now, if it's a constant, fine, that's 2. But if it's an arithmetic operator, you have to evaluate its children. In this case, it's variables. So whatever those values of the variables are, they're added. Now you have these two. Now you can do the division. And now that you have this number, you can do the square root. And so all computation, all programs can actually be represented by an S expression tree like this.
Is that 2.0, is that a fixed number?
2.0 was the numeric constant, yes.
It's any constant.
And the slides from this the slides comes from a presentation. I did this thing, I did some research on how you fix the numeric constants in this tree. And I don't want to get into that because it's just too specific. But you can do hill climbing in other ways. Like, say you got this solution, maybe just adjust these numbers a little bit and you come up with a better solution. So numeric constants the guy who invented this, Koza, was at a conference and he said numeric constants are kind of like the skeleton in the closet for GP because it just puts in random numeric constants. And that's not always the best way to go. Anyway, this is a function here, and this shows the S expression tree that would be represented by this. Now, the
output of that could never be 7 or 8.
Could never be 7 or 8? Well, you don't know what A is, I guess, but...
Well, if A is greater than 10, return 20.
Okay,
Return
well...
A divided by 2.
What this is doing is, yeah, this is returning a Boolean, and then this Boolean chooses one of these two.
No, I'm just doing the, yeah.
The point is, it's not a good function for anything.
Okay.
It's just an example of how even an if statement or for loop could be represented as an S expression tree. And then, and this is the same process as setting up a GA. You have to define an appropriate set of functions and terminals. The functions must have closure. So you can't, like division, we have what's called protected division. So if you try and divide by 0, it comes up with some arbitrary number, but you can't, I would tell the students about this. Okay, so it's a programming language for which there can be no syntax errors or logical errors. The code has to run, no matter what. And then they want to know, why didn't you teach us this language instead of those languages you taught us? Well, it's a horrible language. And if you look at like a page of this stuff, you know, it's just endless parentheses. It's unreadable to humans. So it's not a good language. But essentially, you start off with a random population of these S expression trees. And then you run the program and see how well they do on sample input. So then their fitness score is based on how well they perform. And it's actually kind of cool because we end up with programs and don't have to write them, right? The computer is writing its own programs. So same process. You know, you create the next generation, randomly select elements to just be included, randomly select elements for mating and mutation. Now, how do you mate these trees? Well, if you had 2 trees, you randomly pick a crossover point within the trees, and then you swap the subtrees. And that way you're getting a meaningful thing. You know, if you take a C program and just rip it in half, and take one half and combine it with another program, take the other first part and combine it, won't actually compile, right? It's not meaningful. But once you've got the tree representation, you can end up with offspring that have some of the properties of both of the parents. Mutation is done the same way. You just pick a random point, mutation point, kill off the subtree, create a randomly generated new subtree, and just paste it in place of where the mutation point was. I have tormented you now for 1 hour and 20 minutes. So, I did mention in the little flyer that I would talk about some other techniques. What I've done is I've included links to the Wikipedia page where you can probably get a better explanation anyway. Particle swarm optimization. I guess maybe the neural nets was optimization in the case where we wanted to decide like how much of the portfolio would be stocks and how much would be bonds. But optimization problems are essentially this. You have some function with multiple inputs. and you want to know what inputs will give you the best result, either the highest number or the lowest number. And if you look at this one-dimensionally, you might have a curve that goes like this, and then so you're just trying to pick x because there's only one dimension to this problem. So you could run down, up and down here, and you go, well, this is a good x, but it's not the optimal x. It's a good x. It's a local optima, but it's not the global optima because that would be over here. So the question is, how would you find that? Now that's just one variable. So you could just do a brute force, just keep trying values of x. You could try a random thing. You could try a lot of different values of x. If the curve's pretty smooth, you can do a hill climbing thing, So if you get to a value, like say you got to here, you could step a little bit in both directions, and you would see that going this way is better, right? And if you kept doing that, and then there's the Newton-Ralston method. You could actually, if you went a little bit here and a little bit here, you could actually get a line that would give you an idea of where maybe you should go. And then when you got to here, this would be suboptimal, but you would take a little bit here, a little bit there, and it would give you a line going the other way.
That's
And
interesting.
it actually, the Newton-Ralston method will work really well with most functions, if this is a mathematical function. But what if it's how much stock, how much bond, how much gold, different components to a portfolio, then there is no function. You just have to go back through all the historical data and see how it did. If you had if you had a two-dimensional surface, then the way particle swarm optimization works is you might scatter random points all over the surface, right? Because you're trying to find the optimal x and the optimal y. So if you look at this as a mathematical canopy, up above this xy plane, there's some sort of canopy, and it's a two-dimensional canopy. I can't even draw in 2 dimensions, so forget about 3. But there's some canopy above the surface where if you get to the right xy, you might find the highest peak on this canopy. And the way it works is all the particles they all have an xy value. So I know that this particle is located right here on the xy plane. Now, it's not xy because if it's an interesting problem, there'll be 100 parameters. But if you think I can't draw 2-dimensional, 3-dimensional space, you can forget about 100-dimensional space. But the logic is the same. It also gets a dx dy. And this is like a direction that it's going. It's not only a direction, but it's also a speed. So it tells you what direction it's going and how fast it's going. So all these particles are moving around. They're all moving around in this multi-dimensional space, searching for good solutions. Now, each particle keeps track of the best spot that it's ever been to, the point where it got the best results. So that would be, I'll just say bx, by. We like complicated things in mathematics, but don't let that bother you. So it's keeping track of its xy. So the particle is here, let's just say here, and it's traveling in this direction, and it remembers that right here was the best spot that it had ever been to. Now, the whole swarm, and this is a particle swarm optimization, so the entire swarm also has a best. Because of all the particles, they're all keeping track of their best, and one of those particles has hit the best spot of all the entire swarm. So that's over here. And essentially, this thing is here and going in this direction, but it keeps going in the same direction, but it's slightly attracted to its own local best and also to the swarm's the swarm's entire best. So this vector keeps getting adjusted. So you have this thing here, and you have this thing here. So these are also vectors. So you add, and these, I'm just throwing these arbitrarily out. So you add 5% of this vector and 5% of this vector to this vector. I don't know how that would come out. I'm guessing it would be something more like this.
So I think the direction's gonna be continuously changing though.
Yes, oh, these things, it's fun to watch them, and I've got that here on Wikipedia. I don't know if this
I'm
link
reminded of
will
a flock of birds, you know, when you're.
Well, that's the thing was originally, if you read on Wikipedia, it was originally done to mimic birds or herds flocking. So let me see if
It
this,
looks random, but it isn't. You know?
let me see if this is a live link. Okay, good. And this is a GIF and it's on a loop. Oh, it's really cool. You just have to take my word for it. I don't know what happened.
Projecting all of a sudden.
It says click to exit presentation.
Oh, something. Exit. Click to exit presentation.
Oh, I don't know. Maybe this thing needs to be dragged over. Oh, there is no click to exit presentation. Yeah, it's hard to see from where you are. This thing overheat.
No, it's still displaying. It just says click to exit presentation. Like
Well,
it's,
Tom,
Oh.
remember you extend your screen versus, I think you're showing the
I
wrong
ended
screen
up-
on the projector.
Maybe, and so, but I tried to drag this over to the other one.
I think you need to.
well, click on that to kill the presentation.
Yeah, maybe this is right.
Now I've got 3 screens.
Your screens are swarming right now.
Yeah.
Oh.
Well, I'll send you all those slides.
Yeah.
And you know, if I could just get this back with the internet, the last slide is, but I don't have that anywhere. Let me just see. Okay, escape.
Oh, let's see.
Windows P. Let me go to duplicate. See if I can get. I almost had it. Searching for source. Well, let me go back to extend. Okay. And now let me see if I can drag this over here.
Yeah. There you go.
Okay. So, and he's, you know, and this is not,
Sorry.
he's uniformly distributing these things And you can see the vectors. Some of them are longer, they're moving faster, and some of them are slower. And they're converging at different points. And I guess what he's saying here, I'm not sure, I guess he's looking for the minimum. And so this area being in blue is the lowest, and that's where he's looking for. But some of these other areas are local minimas, and it's having a hard time, like this poor individual here is having a hard time like getting loose from whatever little valley it's in to, you know, hop over here.
So you give it long enough, are they all gonna focus to the center? And
Yeah, maybe.
And when do you stop then?
Yeah.
Whenever you want.
I see.
There are no rules. Like I said, this is alchemy, not science.
Yeah.
And simulation.
It's a gift, so it's just on a cycle.
Yeah.
These numbers here, 5% and 5%, you can play with these. And actually, each particle can have different values.
I mean, it doesn't matter, if most of them are going to one point, then why go further? You got the point, right?
I think that would be the idea is,
Well, what's the most? That's the question.
What's that?
you know,
Like,
you
what is
don't
the
want the
most?
perfect to be the enemy of the good,
Yeah.
right? So if you got to, if you had a bunch of parameters that made you a lot of money,
Well.
you know, why be selfish?
You might end up with 2 or 3 points, but you could pick whatever, I guess. I don't know, just,
Okay, well, it's the nature. See this 5% and 5%.
yeah.
If you made it look for its, first of all, if you made this 0, then this becomes an independent agent. It's off searching on its own. If you made this 1 and made this 10, then it's pretty independent agent, but it has some influence. What they tend to do with this is they tend to start orbiting best values. And so in a way it's good because they're searching around where a good value was. Let's say you found that this set of parameters was profitable. It might be, you know, tweak them a little, you know. So what if this was a little different or this was a little different? And that's what the particle swarm does, is that they're moving. You can even see these guys are still moving. Even these guys are still moving a little bit. But of course, being close to this best here, and which will also be their personal best, so they keep getting drawn closer into it. If you make these numbers, actually, this is true in all optimization systems. You have a conflict between being exploratory or being exploitive of what you already know. And so making this number very high would make it exploitive. So it's going to find something good and then just say, oh, this is good.
Well, that's convergence.
Right. And if you make both of these values low, this thing wanders in space looking for better solutions. So it really depends, you know, it depends on what you're trying to do. And you might make some of the particles very exploratory, because who knows? This may have made a lot of money, but there may be something much better somewhere else. And then you might make this value very high, and that's saying, okay, look, find the best, and then swarm around there and just tweak it a little, because that's what you get when you optimize these. Anyway, there'll be a link in the slides to the, and somewhere, and there's another technique called simulated annealing. Now, that's the trouble with multiple screens, you lose your mouse. And, oh, I see, this is Libre Impress and not the slideshow, which was another thing. And maybe the slideshow ended anyway, this is, oh,
Still seeking.
okay, so this was the animation, this is the article that went with it. This is pretty much what I said, but probably explain it. Actually, maybe the way I explained it was simpler. You know, we have this tendency to make things, simple things complicated, this academics, right? This is simulated annealing, and since before I knew anything about computers, I made jewelry. And so this simulated annealing thing confused the hell out of me, because when you anneal silver or gold, you heat it up till it's glowing red, and then you throw it in cold water, and all the molecules relax. When you anneal steel or iron, you just heat it up. You don't quench it. That does the opposite. It hardens everything. So this simulated annealing was confusing to me for a while, till I realized there's a difference between annealing ferrous metals and non-ferrous metals. Okay, so essentially it's the same thing. You have X, Y, and Z, and you just assign them random values. It's not a population, it's just one individual. And then you change X a little bit, or change Y a little bit, or change Z a little bit. You make some change to this thing, and you measure whether or not it's better or not. Now, if you only accepted it if it was better, then that would be something called hill climbing. It's sort of just you're on a hill, and you step a little bit this way. Okay, now I'm higher, so I will keep going in this direction. But what simulated annealing does, it has this cooling curve, and it starts here. So this is time, and this is temperature. And it starts hot, and it gradually cools down. And while it's hot, there's an increased probability of accepting a worse solution. So even if you change X and it makes it, if it makes F of this whole thing worse, you look at the current temperature and then you take whatever probability is there. So it might be 90% chance at the first, 90% chance of accepting something that's worse. Okay? And then the cooling, you know, you keep going, so it keeps dropping. So as you make these random changes to these values, it becomes less and less likely to accept a worse solution. And for some reason, this does a pretty good job. And again,
what do you mean by a worse solution with jewelry or what? I don't get it.
okay, well, this has nothing to do with jewelry. We're back to the financial analysis. So I'm saying that X is how much stock you have, Y is how much bonds you have, and Z is how much gold you have. And what you're doing is you're doing a historical testing. So you're just saying, if I had those percentages and I went back 20 years, what would the market have done to me? And if I change the percentage of stock, if I lower it, then if I go through the past values, it turns out I made less money. But because the temperature is high, I'm going to go ahead and accept that anyway.
What exactly do you mean by temperature in the stockbook? Right?
Okay, so the temperature, it's simulated annealing. So the process is called annealing.
Okay.
So in ferrous metals, when the temperature is high, the molecules are all loosey-goosey, and the blacksmith can hammer the horseshoe and change its shape, and it's almost liquid to an extent because he can change it because it's hot. And then as it cools, it gets very hard and it won't change. So the idea is that over time, the temperature drops. And the temperature you could just say a probability of accepting a worse solution. So it's going to go from 90% chance of accepting a worse solution down to a 1% chance of accepting a worse solution. So at the beginning, when you just fiddle with random values, make little changes to these things, it might make it worse, but you might keep it anyway because the temperature was high. This is, you know, really start mixing up the analogies. It confused the hell out of me because it's the opposite of what I was used to. Annealing for me was to take the metal, heat it up, and then dunk it in water. And if you do that to silver, copper, or most non-ferrous metals, they come out and you can just sort of bend them with your hand, right? But if you heat it and let it cool on its own, it gets really hard. So, you know, talk about analogies being confusing. You know, I had to understand that ferrous metals anneal differently than non-ferrous metals. So anyway, so here the metal is red hot, and so it's allowed to fluctuate more. Even if it ends up being worse, it's allowed. And then gradually the temperature comes down, so now these random changes only improve the thing. The analogy that somebody showed me is like, you know, really great to mix analogies. Like, say you had a box and it had like a little ball in it, and it has a rough surface inside. Well, if you just vibrate this thing a little bit, the ball's not going to move. But if you shake it wildly, then the ball's going to keep moving around. And it might even be here and jump out. Okay? And the idea is that if you shook the thing really hard, and then you kept shaking it, but you reduced the amount of shaking so that eventually it was barely vibrating at all, you'd probably end up with the ball being down here. Now, it's not as intuitive that this works, but it does, and it's very fast. And so it's almost the first tool that you go to. You know, you could do this with genetic algorithms. You could have like a population of 10,000 of these things. And then they're all being evaluated, and then they're sharing their X's and Y's and averaging their values and getting a new generation. And it's very computationally expensive. This thing only has one, but it works pretty fast. So this is sort of like your first shot because it doesn't cost much. So if this thing solves it, and you know, there's even people question whether simulated annealing even is part of AI. And then the analogy is that when something starts working, it's no longer considered AI. It's whatever it is. It's some algorithm of its own, no longer in AI. AI is the collection of things that don't work. So some people would argue that simulated annealing is not AI. It's sort of just a dumb hill climbing search with a randomness added that allows it to step out of ravines and get to the high ground. So, and that is the last slide. I didn't know if there was going to be time. Here's my email address. Since I retired, I no longer check my emails. So it's a two-step process. You have to call me.
Oh, really?
And tell me to check my emails.
You probably have a secret email, but I don't know.
No. No. I hate email. It's just like, you know, if the Postal Service operated the way email does, you know, and every day the postman came with a dump truck and just dumped like loads of crap on my lawn, I'd get a court order to stop it.
So
But-
your preferred method of communication is phone.
Yeah, but if you got something you want to send me, I'll find it if you call me. Which is weird because when I did the YouTube video, I think I mentioned that, but I did leave my phone off. You know, the nature of the internet is like, you're crazy, you're stupid. And I don't care what people put in the comments, but I just don't want them calling me. So I don't know, maybe I should start. What I should have done is said, send me an email and include this in your subject line. Because I'd be willing to search occasionally for a given subject line.
There's a third possibility, text message maybe.
Yeah, this will work with text messages. But you know, for some reason my phone is like beeping and booping all the time. And then the few times that I go and look at it, it's like, it's high tide in Honolulu or something.
Yeah, I noticed it. I shut off a lot of things so that my battery, it saved my battery, because I never know what it is. Something
I like
goes
do
in
not
there.
disturb. I just put that on.
Well, yeah, no,
And I guess my kids are on the list where they can get through the do not disturb. I don't know. I
right.
don't know. I just, you know, I always thought email was just a way of dumping work on people. And before I retired, it was, right? I mean, students email you and you can't ignore them, right?
And there's Facebook messages.
What's that?
Facebook messages.
Facebook Messenger. I am on Facebook. So,
I'll write that down. What's the, if we want to see the video, is there a
Oh.
name we put in with it?
let's just see.
Or can we just find it by your name?
If you look up particle swarm optimization, this Wikipedia page will be at the top of the search. And if you look up simulated annealing, this Wikipedia page will be at the top of the search. What I'm not sure of is if I click on it, whether or not what it'll do to the projector.
This video.
Is it going somewhere? Did it go over
Looks like
here?
it just took you into editing the link.
Okay, well, hang on. The only problem is well, this doesn't look too bad. The problem is the multiple subscripts confuse people. So I described this for one particle, and so then you get, you know, subscript N and M, and you know, on and on it goes. So, oh, you know, if you're interested in this stuff, I think I left my briefcase in the other, because I have a book that I can recommend. It's not my book, but I mean, I own the book, but I didn't write it.
I took a picture of it.
This is one of the best AI books that I've found. Not that it's perfect, but it's AI Application Programming, second edition. There may be a third edition by now. Comes with a CD and all the code. And here it's doing the neural networks. And it's got the code for the neural networks. The code is what I'm not so thrilled with. The code, it reminds me of BASIC that's been converted to C. So a lot of drop through code, like look at this, it's int main, and that's the whole thing. There are no functions, there's no, and so the code is horrible. And so in the class that I taught on AI, a lot of it was like rewriting the code. Then I would have my own object-oriented version of the same code where every particle is an object and it has these properties. And then I realized my code, like for somebody to just look at it, you couldn't understand what the hell it did. Where this guy's code, because it is all one block without any function calls, you can sort of read it and figure out what he's doing. The other thing you can do with this code is you can take his code and encapsulate it and put your own, so that when you need simulated annealing, it may be horrible code, but at least it's encapsulated so you don't have to look at it. You can just call it. So this is the book, and I went through a lot of books teaching AI. And the first time I looked at this book, I was in a bookstore and I looked at the code and just went, ugh. It's like, use a bunch of pound defines for variables and stuff. That's not modern coding technique.
I'm sorry, are you talking about a specific language?
Yeah, he does all of this in C.
Oh, it's in C, okay. I just,
Yeah. Just snap a picture.
Sure, sure.
Thanks.
I'll throw a picture of it up on those. I'll put a slide with a picture of this. And so it's different from other AI books. Like AI, like all that that first stuff I did, you know, the A-star search. Like a lot of AI books will go on with complicated proofs that this will find the optimal solution. And you know, most of the students were going, you know, you say it's proven, take your word, you know. And so more, this is book, see, as AI application programming. So it's more about the programming aspects of actually getting the stuff running as opposed to being theoretical about it. So actually, I think it's good, and it covers a lot of subjects that I did not cover here. So, AI Application Programming by M. Tim Jones. So, and this was the second edition. The first edition left out all that finite state stuff. So it skipped that, and now it has a chapter on that. And it's just, you know, I think it's a good book. You know, without becoming, you know, too deep in the mathematics. Occasionally, there's a bug.
For $7 to $12, you can't really go wrong.
$7 to $12
For a used copy.
That's great. Make sure it includes the CD.
Ah, right.
So, something you probably want, because the major error that I found was there's a certain point where it calls a random number and then it uses that to index an array. And the way he called the random number, he might get one number larger than the array and then the whole thing crashes. So you might watch for that, you know, but it was like a bug we fixed. So
Yep.
wasn't the end of the world.
Okay. Yeah, do you have any like recommendations or warnings as far as where to get started if we have something? Like, I think there's like a thing for Python called TensorFlow. Is that?
I'm sure there's
Any good?
Python code for all of this. In fact, on the wiki page, I think there was a link, or when I did a search, there was a link for Python. Everything is in Python.
Oh, it was just one example.
Yeah.
It has
I've got a-
giant libraries of everything imaginable.
Okay, so it's not a bad place to start, perhaps.
Perhaps. I wouldn't pick Python as the ultimate language. The problem is, something like C or C++ runs native machine code at the end. And Python is interpreted, so you're going to lose some performance. And performance may be ultimately an important thing.
Sure. Okay.
So,
Well,
on the other hand,
so-
Python is a really cool programming language. And so you don't have to get tied up in the complexity of the language when you already have enough problems with the complexity of the problem,
right.
And then you get into stuff like C++. So now you got that double complexity. Yeah, Python's very cool.
It's all a judgment call, basically. That's fine.
I learned Fortran, didn't like it, and then learned BASIC, and it was like so easy that I spent a couple years just playing with BASIC, and then I learned Pascal, which was a lot more complicated, but also a lot better than BASIC. So you really started to understand the weaknesses of BASIC. And then the industry went to C, and then C++, and now I'm doing C# because it's the best language
Aren't
there is.
functional programming, beta machine learning, like Lisp?
Yeah, Lisp was the language of artificial intelligence. And even you'd go to conferences and they'd present all their code in Lisp. But then when you talk to them, they go, oh yeah, well we did that in the paper, but actually we wrote this in C++. So the performance of Lisp is not that great. Again, highly interpreted. But a super cool language. Although Schema is a more modern version of with the Lisp concept. Very, very, very cool. I just blew my mind a little bit learning Lisp.
It's weird and fun.
It's weird. The worst part of Lisp, and the reason Lisp is not really a good language, is that it does a lot of macros. So you don't write the code for something, you write the code that writes the code that does something. And it in turn might call macros in the process. And that's really great, unless it doesn't work. And now the debugging is a nightmare because you know the final code that it wrote didn't work, but you've only got the code that wrote the code, not the code itself. So yeah, that's, but it has a certain intellectual appeal, and that was from the beginning. Fortran and Lisp are the two oldest languages, and Fortran was the scientists and the number guys, and Lisp was the AI guys. So
Write a lot of spaghetti code in Fortran.
yeah, Fortran. Had a couple semesters of Fortran back in the day. Punch cards.
Oh, yeah. But you
I guess my final comment is you can write a lot of crappy code in any language. And,
Mountains of crappy code.
yeah.
I think you get better with
Well,
time.
thank you, Tom.
Yes, well, thank you, Wayne, and guys, everybody have a super day. If you want to call me and talk about this stuff, I'm not doing anything. So.
Yeah, I want to talk about this stuff.
Well,
Yeah, thanks for coming.
give me a call.
Thank you.
I am now going to stop the recording. 2 hours. 1 hour and 59 minutes.